Good afternoon again. Thank you all for joining. I'm very pleased to introduce the speaker of our MoD lecture today, Professor Dr. Stephanie Evert. Stephanie is a professor here at FAU. She is running the chair of Computational Linguistics, Computational and Corpus Linguistics. Actually, she has a background as a bachelor in Stuttgart in mathematics.
A diploma in mathematics.
Well, okay. So she will tell us more about the trajectory. But this is a particular case of successful path in which from math you can get, impactfully into different areas like in this case, computational corpus linguistics. So Stephanie is the vice-spokesperson of MoD. So she has been with us from the very early of the conception of the center, that, as you know, was built as a merging pot or a point of intersection of different groups and disciplines here at FAU. Certainly, that is all related to mathematics and data science, artificial intelligence, computational mathematics. So these link us very naturally to other groups, like the groups in computational mechanics here in the Faculty of Engineering, Computer Science, and so on, but also through machine learning to computational corpus linguistics. Probably this is a very superficial understanding, but if somebody had any doubt that there was a link between linguistics and mathematics, now well, check ChatGPT and you will see that indeed, there is a connected path of a steady configuration that leads you from one configuration to the other. So Stephanie Evert, before she's a transgender woman, so you want to find her full academic achievements, you will have also to pay attention to the fact that earlier she was Stephen Evert, so you can see this name change. Which nowadays that counting in Google Scholar and so is so important makes is not totally irrelevant, right? So I hope this has.
I'm still not sure how well Google Scholar has.
Are they counting well or not?
I'm not sure whether it gets. It seems I still have difficulty getting a few of the new papers, although I've specified both names there.
Definitely.
Best thing is to use APA-like citation, so you just have abbreviated first
names.
We
have this problem also because we use two family names normally officially, and then in the standard international system they only take the last name. So many people in Spain have to merge both names to make one full name, so that these systems recognize your work properly. Anyhow, so we are very delighted. And today, in principle, we are learning about this field in a way that we, in particular us, as very simple-minded mathematicians can understand. Thank you, Stefan.
Yeah. Well, thanks very much. So today I'm going to talk about a topic from my research field of computational corpus linguistics, which means there will be a lot less mathematics in this talk than you're used to from the lecture series. Instead, we're going to look at linguistic research questions and certain fairly simple quantitative techniques we can use to find evidence to answer these questions. So thanks very much for coming anyway. I hope it'll still be interesting. And there's a little bit of math there too. Okay, so the research question I'm addressing actually is situated in a division, in an artificial division that has a long tradition in linguistics. It's sort of something that we've overcome in the field, but for a long time, people used to think of linguistics as a division between grammar and lexis. So lexis is the vocabulary, the words. Lexis is dealt with in dictionaries. Grammar is dealt with in grammars of the language, often prescriptive grammars that tell you what the right way is to form sentences from the words of a language. Grammar and lexis were seen as two entirely different fields or different aspects of language because grammatical rules are fully schematic and productive. That means they are regular. You can apply them in any case. You can form many new sentences using these rules, and they apply in a completely regular and transparent, or as we say, compositional manner. Compositional means that the meaning of a sentence, when you use a grammatical rule to form a sentence, the meaning of the sentence can be derived from the meaning of the parts. So there's this, it's meant to be unambiguous, that you can get to the meaning of the sentence from the meaning of the parts. On the other hand, the vocabulary, the lexis, was always seen as completely fixed and arbitrary. So the relationship between words and their meanings is arbitrary convention. That's why we need to list all the words of the language in a dictionary. The words are fixed units. We cannot, well, we can create new words, but people tended to ignore that a bit and see the words as these arbitrary fixed units. And their meaning is that the words are entirely specific, are completely specific. So they have a very precise meaning, or perhaps a small number of meanings, whereas grammatical rules have this general schematic structure. And correspondingly, the fields concerned with lexis is the field of lexicography. By the way, we're also teaching lexicography at Erlangen and computational lexicography. That might also be an interesting point for collaboration or option for collaboration. And the field that has specifically dealt with grammar is theoretical linguistics, basically from 1957. That's when Noam Chomsky published his PhD thesis and basically turned around theoretical linguistics to focus entirely on grammatical structures, ignoring both meaning and lexis, until around the 1990s, when things started to change again. And one important reason for that change is that people began to realize, or could no longer ignore, the fact that this artificial separation of lexis and grammar is inappropriate, and then actually there's a continuum from the fixedness of lexis to the productivity of grammar. And this is the fixedness productivity continuum that's at the heart of this talk. I already mentioned that words actually, that words aren't completely unproductive, because no language has a finite vocabulary. We can always create new words. For instance, the English word train station is actually made up of two existing words, train and station. It's such a well-established concept that we often think of it as a single word, and it's represented as you'll find it in the dictionary listed as a single word, but it can be formed from the individual words, and we can form many other words in a similar pattern. So there are productive morphological patterns that allow us to form new words, which shows that even the lexicon isn't entirely fixed. There are still schematic rule-based processes going on there. Then people have also realized and that's a field that's very close to my own research. Phraseology deals with multi-word constructions, multi-word units that consist of several words and often show some flexibility. I'll have some examples of these constructions on the next slide, so I don't want to spend too much time on that now. My own home field, so I have these two homes in computational linguistics, which is more from the mathematical and computer science side, and corpus linguistics, which is sort of my linguistic heart, and also a lot of mathematics, because we do a lot of statistical analysis dealing with corpus frequency data. So the field of corpus linguistics has always been interested in that middle of the lexis grammar continuum, in dealing with phenomena that cannot be described either by a list of words or by a simple set of grammatical rules. And more recently, the research area or the approach of construction grammar has become extremely popular, to the point that it's almost at the point of becoming a new dominant paradigm, or a very popular paradigm in theoretical linguistics. Construction grammar posits that there are neither words nor grammatical constructions, but rather that everything in language is a construction. And a construction is a pairing of form, the linguistic surface form, often partly schematic, partly fixed, partly specific, with a specific meaning. So I'm going to talk about constructions today. We actually have a research training group on construction grammar, dimensions of constructional space. The first cohort is in their final stages of writing their PhD thesis, and we're getting a lot of exciting results in this area. So
the placement of these keywords along the horizontal
that's sort of
axis
where they are. So construction grammar deals a lot with constructions that are strongly syntactic, have a lot of syntactic component or grammatical, and less with constructions that have many lexical elements, whereas phraseology deals with constructions that mostly consist of fixed or restricted lexical elements. So that's an attempt to place them. Of course, it's difficult to place them precisely. But that's the kind of background against where
and corpus linguistic is the envelope of all of them? Or?
No, corpus linguistics is where my kind of corpus linguistics is a special, very specific field that deals with corpus data. So in one sense, as a methodology, corpus linguistics applies to almost all of modern linguistic research and has a very important role in construction grammar as well. On the other hand, there are also specific research questions right in the middle between lexis and grammar that are core to corpus linguistics and that are also important to my own research. But let's turn to some examples of construction so you get a better handle on this. And today I'm going to talk about fixedness, about this fixedness productivity continuum for constructions. There's one specific constructions we're going to focus on, but here are some other examples of construction. A very lexical construction close to the lexis end of the continuum is the emotional baggage construction. This is often given as an example of a collocation in English because there are two near synonyms, baggage and luggage, but you cannot say I'm carrying around a lot of emotional luggage. You can only use that collocation with baggage. And that's has always been taken as an indicator that this is collocational, a collocation in the sense of a lexically determined construction, that you don't have free choice as grammar would posit it traditionally. You cannot freely combine adjectives and nouns. But sometimes we have typical combinations such as emotional baggage to the extent that the expression emotional luggage would be difficult for native speakers to understand. But when you take a closer look, it turns out it isn't just a single collocation. It's actually a somewhat productive constructional pattern because there's a range of other adjectives, ideological baggage, spiritual baggage, intellectual baggage, which clearly use the same sense of the noun baggage, the same metaphorical sense of baggage, or evoke the same metaphorical sense. So I think of this emotional baggage as a construction that allows a certain range of adjectives that are also semantically quite similar. One way of describing such a construction, so this consists of an adjective where we have a range of different adjectives. So that's a variable, an open slot of the construction, and a lexically fixed element, that's the noun baggage. So we can describe this as X baggage, where the X marks the open slot. A German example, I'm afraid I have to give a German example because German morphology is so much more interesting than English morphology and so much richer, and especially because German recognized that things are morphology because we write these long units as single words, whereas in English we separate, noun compounds are separated and often treated as part of grammar. But anyway, this is the itis construction. As you all know, the suffix itis can be used to describe inflammatory diseases such as pancreatitis or arthritis, etc. Same in English and German, but in German, and as I just found out by looking at the dictionary today, also in English apparently, there's a non-medical version of this construction. We can use it to indicate that somebody is doing something too often or doing something too much. For instance, the German Telephonitis, I think that was the most popular form of the construction, at least when I grew up. That was a very popular word, was used to describe people who just spend all their time on the telephone, ring up other people too much. And then we have something like Subventionitis, too much subsidies from the state given by the state, etc. And as you can see, again, it's not just these. I used to think of that as just, well, a creatively formed word that became popular. But when you look at a corpus, data, you see it's actually a productive construction. You can form many new words, and people have invented many words with this itis construction. So this could be described as an X plus the suffix itis. It's plus because that's fused into a single new word. Another example is the X is the new Y construction. I'm not sure. I think the original form of that, I'm not sure whether orange is the new black was the origin of that construction. Basically, black is the default or most popular color in fashion. So if you say something is the new black, means something is so popular, it could replace black as the favorite color in fashion. So you find white is the new black, orange, denim is the new black, being Irish is the new black, as anything that's popular can be described with this construction. So that would be another construction, X is the new black. But if you look further at corpus data, then you realize that also the second element, black, can now, because once this has been established well enough as a construction, the second element can also be replaced. So you can say something like comedy is the new rock and roll, and people will understand it in the same way. So here we actually have a construction, X is the new Y, with two fairly variable slots, fairly productive slots. And it's actually the score of is the new that allows us to recognize this construction. And this can go in further to have even more slots and even more flexible construction, the X earns YZ construction. That's actually one usage of the word earn. Normally you earn money, but you can also say that somebody, say this success earned him recognition. So something earns somebody something. And that's one particular usage of the verb earn that also has some specific meaning components and some certain restrictions on these slots. But basically, we're very flexible in what can go into the slots X, Y, and Z. So this is actually construction with 3 variable slots. Now, what I want to talk about is the question to what extent, and so the first construction I gave you, X baggage, that's a fairly restricted, a fairly fixed construction because there's a fairly limited list of adjectives that can occur in the X slot. The itis construction is much more productive. X is the new Y is even more productive because X can be basically anything that makes sense as something popular or that happens to be popular. So these are actually in different places on the fixedness productivity continuum. So what I want to talk about today is how can we measure this or how we can place constructions in this fixedness productivity continuum. A first important realization when you look at X is the new Y or X earns YZ is that it's difficult to speak about the fixedness or productivity of a construction as an entire unit, because what's productive, if you consider the X baggage again, what's productive is actually a variable slot within the construction. And the productivity of these slots might be quite different. So the X slot will be highly productive because we can insert basically everything. To what extent the Y slot is productive is actually an open question. I haven't taken a closer look at the construction. I'm sure somebody has in linguistics, but I'm sure that the Y slot is much more restricted in what you can do so that it's still clearly recognized as the construction. And that means that we can just talk about individual slots. So that's what I'm going to do today, talk about fixedness productivity continuum for a single slot of a construction. And the construction I want to look at is a construction that has been called a shell noun construction. It's the combination noun, the verb be, the auxiliary be, and a that complement clause. So here a typical example, which I'm afraid is true, is that the fact is that you'll have to listen to my entire talk today. So here, what makes this construction special? So it's nice for us that this has a single variable slot or a single essential variable slot, namely the noun, the shell noun. What is so special about this construction is that this shell noun functions as a conceptual shell for a complex piece of information expressed by the that clause. And it allows us to address certain or assign certain meaning aspects to that complex piece of information. So here are a few examples. The problem here is that having so easy access, it's very crowded at holiday times. So the complex information is basically it's crowded at holiday times. And what the shell noun does is indicate that this is a problem. But the fact is that very lack of evidence seems to fan the flames of suspicion. The complex information is that lack of evidence fans flames of suspicion. And this is indicated as being factual. It's that as being true information or something we have to accept because it's a fact. And finally, our main concern as a group is that we do not waste the money. So the complex information again is wasting money. And then this is, and here you can see that some more complex aspect or meaning aspect is assigned here. It's marked as a concern, but not generally as a concern, but a concern for us as a group, for a specific group of people. So that's how this works. So that there's an entire book about shell nouns and shell noun constructions. There are four main constructions, and we picked one, which is this noun plus be plus that clause, because it's fairly easy to recognize, and we wanted a clear-cut case, for example. So the goal of this research I'm presenting was to explore the fixedness productivity continuum for the noun slot of this shell noun construction, the noun be that construction. You could also focus on other elements on the constructions, for instance, the verbs that occur in the complement clause. So what's kind of the key complex information expressed? Here it's about something about wasting. Here it's about fanning flames of suspicion, etc. So this could equally well be done, but of course the core of the construction is the shell noun, and that's what we're focusing on here. One interesting aspect, especially from a linguistic perspective, is that Hans-Jörg Schmid, who published the book on shell nouns in the year 2000, has identified 6 different semantic classes of shell nouns. We are going to focus on the first 3 of these listed in the first line here. So one class of shell nouns expresses a factual aspect. So that's nouns like the fact is, the thing is, the problem is. So that either establish this as a fact or addresses some other factual aspect of the information. Then there are mental shell nouns, so a class of mental nouns like the idea, so our worry is, that describe mental processes involving that complex piece of information or mental attitudes involving that piece of information. And finally, the linguistic class of shell nouns, they describe, they show how the information is expressed or address the information as expressed in language. Sort of our promise is, so a promise is something that you have to say to make the promise, or the story is that turns the information into a specific story, into a narrative that's then expressed. And then there are 3 other classes. The first 3 classes, factual, mental, and linguistic, are the most frequent ones. So these are the ones where we can actually carry out a quantitative analysis. The other 3 classes are too infrequent for in the sample that we've used. So this opens, the fact that we have these 6 different shell noun classes opens a secondary research question, namely whether there are differences between these classes. Is there evidence that one of the shell noun classes is more productive than the other shell noun classes, or can we see any other differences? Okay, in order to carry out quantitative work, we need data. So as I'm not an armchair linguist, as they're sometimes called, people who just sit in armchairs and ruminate about theoretical linguistics, I need data. We use the data set obtained from the British National Corpus. The British National Corpus is a reference corpus for British English. It tries to give a representative, it tries to provide a representative sample of all aspects of British English, which means it also includes spoken material, including spontaneous conversation. It has personal letters, it has academic papers, it has newspaper articles, etc. They try to cover all aspects of the British English language. That makes it very nice for research. Unfortunately, it's a bit dated. It's from the early 1990s. It was the only time that somebody managed to produce such a reference corpus for copyright reasons, matters of expense, etc. There is no similar reference corpus new reference corpus or reference corpus for another language or language variety. So in order to identify this noun, is that the noun be that construction? First, essentially, it's a syntactic pattern, a noun with the copular verb be, and then a that complement clause. In order to identify such syntactic patterns, we use an automatic syntactic parser. In this case, this was done several years ago, so we still use a fairly old-fashioned parser, which doesn't use any deep learning or AI components, but good old-fashioned statistical parsing, which was run over the entire British National Corpus. The data are actually accessible at treebank.info. That's a website set up by two colleagues of mine at Erlangen. And basically here you can see, practice pointing. Here you can see the structure that we use to extract the examples. This is the shell noun. It's the subject of the copular be. And then the complement of be, that's actually a verb. That's the main verb of the complement clause with the that complementizer. And here there's another dependency to the that as a complementizer of that clause. So basically by running this pattern over treebank.info, we extracted 32,097 matches of that pattern. We have to say matches of the pattern because not all of them are instances of the construction. There are parsing errors, there are sentence duplicates. And then, of course, there might be many instances where we have this syntactic pattern, but it's not a shell noun construction because that's not a shell noun that's used, there's some, it's used in different sense. So in order to have a reliable ground truth for the analysis, I had to find somebody. That's always the point where we need to find a linguist who likes to do a lot of manual work. Fortunately, I had Sasha Diversi to do that, another colleague from the University of Montpellier. And he manually validated a 10% sample, 3,200 examples from the corpus, because going through all 32,000 would be nice, but it's really time-consuming work. So we took a 10% sample. He checked all of them, did some corrections, and so in the end we had 2,500 instances of the shell noun construction. And it's these instances that we're going to analyze now. I'm not sure what kind of data sets you're dealing with in your research groups. I imagine they might be larger data sets in many cases. I also love to work with billion-word-sized corpora, but if you want to, for more sophisticated analysis that involves manual annotation or manual checking, we have to work on these very small samples. Okay, focus is on the noun. Basically, we extract a data table which contains the relevant element. At the moment, we're just going to focus on the noun slot. And then basically we have a list of all the nouns that occur in this construction. And we have identified the shell noun classes for these nouns. Okay, first thing you can do probably the most obvious thing to do is to look at a frequency table of the nouns, because some nouns occur quite frequently. So for instance, we have the point is that with more than 300 occurrences in our sample of 2,500 instances, so this is an extremely frequent instance of the shell noun construction. And we have the problem is, the thing is, the reason is, the fact is, etc. You can also see that the frequencies drop off very steeply. So we have a very skewed frequency distribution, which statisticians often don't like unless they work on these kinds of skewed distributions. But this is very, very typical of language data. In language, it's known as Zipf's law, that we have usually when you look at any linguistic data, there are a few very frequent items and a lot of very infrequent items. Of course, this is just the head of this frequency distribution. If we look at the entire frequency distribution, it's so much longer because we have, so these were the first 40 most frequent nouns, but we actually have 308 distinct nouns occurring in the shell noun construction in our sample. If we had all items around 25,000 from the entire BNC, then of course we would find even more distinct nouns. In linguistics, we usually make the distinction between types and tokens. So types are the distinct nouns and tokens are the instances of the construction. The notation is n for the number of tokens, that's our sample size. and V for vocabulary size for the number of distinct nouns. So we have 308 distinct types. And here it's much clearer how extremely skewed the distribution is than in the first bar plot. So at the very left, we have these first few types that are extremely frequent. And then we have this extremely long tail over here. So all these types from rank 160 to 308 occur just a single time. That's why the bars are so short. And then there's a second group here of types that occur just twice, nouns that occur just twice in our sample in this construction, etc. So we have these totally different ranges in frequency distribution. And one conclusion, or one obvious conclusion from that, is that we have the entire fixedness productivity continuum in this single slot of the construction. Because what we see on the right-hand side, types that occur just once, they're indicators of productivity. Because this is clearly not a construction that people have learned, or people haven't learned that these nouns can occur in the construction. They must have productively, spontaneously inserted them in order to express a certain meaning component. On the very left, we have some very frequent types, which are indicators. High frequency is always an indicator of lexicalization or fixedness. So we know from psycholinguistic studies that any phenomenon in language that's frequent enough will be stored as a unit in the mental lexicon. So the point is that it's certainly stored as a separate construction. So these two parts of the frequency spectrum are fairly obvious. The question that's still open is what happens in the middle of the frequency spectrum. What about this bend here? Well, these are types that are not frequent enough to be completely fixed or unlikely to be completely fixed. But on the other hand, they are also more frequent than you would expect from a completely productive formation. And this is where we have, this is actually what is called collocational patterns in corpus linguistics, and that happens to be one of my favorite research topics. So this is actually a form of statistical associations. These nouns seem to be attracted to the construction. They occur with unexpectedly high frequency in the construction, and often they are seen as fairly typical by native speakers. So my proposal is to understand the fixedness productivity continuum as consisting of three ranges characterized by fixedness, association, and productivity. And that's the approach we're going to take. So as I said, fixedness, the main indicator of fixedness is very high frequency, and it's just very likely that something like the point is, which accounts for 15.2% of the instances of the tokens, of all tokens of this construction, is a lexicalized subconstruction. That's a fixed construction, and it's different from sort of the productive noun is that shell noun construction. Then we have this group of nouns that are unusually frequent, so they seem to be attractive. And if you give them to native speakers will tell you, yeah, that sounds just right. That sounds like the right way to do. If you look for examples of that, if you find examples of that construction in a dictionary or a research paper, they are likely to involve these collocated nouns because they just sound very typical, and whereas the productive ones might sound quite unusual. And finally, we have this long tail of productive nouns, especially where the main indicator is if there are a large number of so-called hapax legomena. A hapax legomenon is a word or type that occurs just once in a sample. A dyslegomenon, a type that occurs just twice. So we have, for instance, the achievement is, the crew is, the deal is, or the basis is, the flaw, our proposal is to. These all sound perfectly natural there, but still they are extremely infrequent, so they seem to have been created or chosen spontaneously. Now the rest of the talk will be concerned with the quantitative description of this continuum, which actually has two essential challenges. One is that we can't divide the frequency distribution a priori. It would be nice if you could say, well, we have a few fixed types, then we have a few associated ones, and the long tail, that's productivity. But there is no clear separating line where the ranges are separated. And the second problem is finding appropriate statistics to measure each of these phenomena in the first place. Okay, so we'll turn at each of those, we'll look at each of those in turn. Part 1, fixedness. So here again is the frequency table of the most frequent nouns expressed as the absolute frequency. So for instance, point with 379 occurrences in the sample, and the relative frequency as a percentage of all tokens, so 15.2% of the tokens. Now, I would argue that we have 3 nouns here that each account for more than 5% of all instances of the construction. And sort of my gut feeling or my intuition would be that these are very, very likely to be lexicalized, because if something is that frequent, it's that dominant that it accounts for a substantial proportion of all instances, it's likely to be established as a construction in its own right.
What do you mean by lexicalize here?
So that it's actually stored as a separate construction, that we have a construction, the point is that, a construction, the problem is that, a construction, the thing is that. And these aren't just instances of the general shell noun constructions, but are stored as separate constructions that often take on additional meaning.
But these are then gathered where in the dictionaries, or how do you recognize?
If we do a sort of if you create, so we're actually working on creating a constructicon. That's the construction grammar version of the dictionary, which lists constructions. Okay. And in a constructicon, we would have the general or productive shell noun construction, perhaps sub-constructions for the 6 semantic classes, and then the lexicalized constructions. The point is that construction.
But this corresponds to the English, right? So this doesn't mean that this will be translated to any other language.
Not at all. This can be language specific. You can look for similarities between languages, but it's
on English.
Yeah, you can always only work on a single language. Because there are always divergences. If you look at that, we would have to look whether there's how the similar construction or corresponding German construction works. We would probably find we might find different shell noun classes, and we might also find that there are different lexicalized constructions.
And there is a concept of distance between different languages, in the sense that how likely it is that these kind of lexicalizations can be translated to others, or is a metric or not?
People do that in language typology. They actually try to identify language families and often have phylogenetic trees of how closely languages are related. But that's often based on word lists and a very limited view of the language. And it doesn't really generalize. So we have some things are very similar between English and German, but other aspects can be totally different. For instance, word order is totally different in English and German. So you can't make a general statement that 2 languages are very similar or dissimilar. You have to answer that question for individual phenomena. Okay, so anyway, from the frequency list, I would say the first 3, intuitively, the first 3 are good candidates for lexicalized constructions. The problem is intuition is not a good mathematical concept, and I can't give any mathematical reason for that 5% boundary. So we need additional evidence for lexicalization or non-lexicalization. Well, one good evidence is polysemy, that's ambiguity in meaning. And so it turns out when you look at the Hans-Jörg Schmidt's book on shell nouns, he gives long lists of shell nouns for each of the classes, but 2 of the most frequent ones, namely point and fact, actually occur in multiple classes. So point can be factual. If I say the point is, I can kind of mark that as a fact. But it can be linguistic. So the point is in the sense that this is what we're trying to express here. And it can also be seen as a mental, assigned to the mental class. The point is in the sense that this is what I'm thinking about or what I see as an important, as the central aspect. And it's very difficult to distinguish these for individual instances. So often you can't tell for a specific instance whether it's meant as factual, linguistic, or mental, or perhaps expresses all 3 components. And similarly for fact, we have factual and modal classes, which means these are actually functionally polyvalent. They can have multiple functions and often might also express a mixture function. And this kind of polysemy meaning ambiguity or multiple meanings, that's often an indicator of lexicalization. Lexicalized expressions are more likely to become polyvalent and polysemous because they're sort of something where we can store this knowledge about their polysemy. If this were productively formed, it would be very difficult for speakers to recognize the polysemy, etc. But if it's a well-established expression, it's easy to associate that. So here, actually, that's a completely non-mathematical argument, of course, a linguistic argument why for point and fact as lexicalized expressions is their polysemy. So that means I have point and fact, and problem and thing as additional candidates based on a frequency. What other quantitative evidence can we find? Well, a second, I already mentioned Zipf's law. That sort of in linguistics, we always get these skewed distributions with a few very frequent items and a long tail of very rare items, or rare types. But actually, Zipf's law is a very specific mathematical law. George Kingsley Zipf proposed in the 1940s that there's a power law relationship between frequency, that the frequency distribution is described by a power law relationship. So if you arrange any linguistic phenomenon, sort of the different types of phenomenon by descending frequency, R is the Zipf rank, that's the frequency rank in this table. Then the frequency of the rth item is basically R to some power, 1 over R raised to some power A, where A is larger than 1, so that we actually have a fall off that's big enough for a very large number, infinite number of types.
This was again for English, or this is a general
Originally for English, but he looked at samples. It was done, so this is a frequency analysis back at the time that was done entirely by hand. He started with English, but looked at other languages. He looked at word frequency distributions, other kinds of frequency distributions. Of course, in the meantime, people have done that for almost all languages and many different kinds of linguistic phenomena. And surprisingly, we always find that in principle, Zipf's law is a fairly good fit to that.
But the exponent changes.
Fairly good in the sense that it is far from exact. It's not an exact power law, and that's sort of, it often seems to hold in the middle frequency range, but not at the top and the very bottom of the frequency spectrum. So there are limitations there, but generally Zipf's law seems to hold up fairly well. So by this reasoning, if we believe that the natural language phenomena, that's fairly interesting stuff about possible explanations for Zipf's law, which we can talk about in a discussion if you like, or over coffee. But if we believe Zipf that this is a kind of universal law of language data, then it should also hold for our distribution of nouns. You all know what to do, right? Double logarithmic plot, because then the power law relationship becomes a straight line. And this is the plot we get for our noun slot in the shell noun construction. So the dots here, the dots here, these are the individual nouns. That's the most frequent noun: point, problem, thing, reason, etc. And then we go down, the bars down here, those are the apex legomena and the dyslegomena with the same frequency counts. If we fit the Zipf-Mandelbrot law, so this is actually a version known as Zipf-Mandelbrot law, an extension proposed by Benoit Mandelbrot. If we fit that to the data, you can see that it's a fairly good fit for such a simplistic law, and given the complexity of language data, except for the very top of the frequency range. So for the most frequent nouns, they're much more frequent than predicted by the Zipf-Mandelbrot law. And one possible explanation is that's because they're lexicalized. As soon as something is lexicalized, it's its own unit. Its frequency becomes completely independent from the productive construction. We could have a productive construction that's extremely rare, but the point is that as an established phrase that everybody uses, that's extremely frequent. So I argue here that types that don't fit the Zipf-Mandelbrot law are evidence that, this is evidence that these might be lexicalized types. And as you can see, it applies to the first 5 types. So point, problem, thing, reason, and fact. So now I have collected fairly good evidence for these 5 nouns as lexicalized subconstructions, because from Zipf's law, they're all 5 seem to fall out of the Zipf law. whereas point, in fact, additionally are polysemous as an additional source of evidence. Is there something else we can do? Well, there's one more phenomenon that's associated with lexicalization. Oh, sorry, that's the 5 one instead. Repeat. There's another phenomenon associated with lexicalization, which has often been called term clustering. So Ken Church, a famous computation linguist, put this in a very nice paper title in year 2000. If he had published the paper this year, he would probably have called it sort of random. If the document is just a random collection of words with usual binomial distribution, the chance of seeing 2 occurrences of Trump should be close to p squared. But actually, when you look at actual data, it's rather p divided by 2. That means once you've seen Trump once in a text, there's a 50% chance it will occur a second time. That makes sense because if you mention a person, you probably want to talk about the person and will mention that person again. So that's how language is quite different from binomial distributions. That's an important problem because a lot of the modeling we do in computational linguistics, traditional statistical modeling, has assumed binomial distributions. So this has always been seen as the term clustering problem. But of course, it's an interesting source of evidence. We can apply the same to the shell noun constructions. If a particular shell noun is lexicalized in a construction, there should be a higher, we might expect that it tends to reoccur, that it's an expression, if you choose that once in your text, because that it's activated in your mind and you keep reusing it. Whereas when you do something productive with a productive construction, the next time you need that construction, you'll have a different need to, you want it to express something different and will pick a different shell noun. So this can be measured in terms of what corpus linguists call dispersion. That's basically how well the occurrences of a particular noun are distributed across different texts. I call this the document frequency. So F, that's the token frequency, how often a certain shell noun occurs. And DF, that's the document frequency in how many different texts it is found. So for instance, the shell noun point occurs 379 times in our sample, and these 379 occurrences are in 286 different texts. So some texts contain multiple instances of the point is that, some texts contain multiple instances of the problem is that, etc. This is not entirely unexpected because there aren't that many texts in the British National Corpus, so that just by coincidence, by the binomial distribution, we would also find such repetitions. So one way of measuring whether there's a term clustering effect is to identify, what I've done here is identify how many occurrences are in texts with repetitions. So 157 of the occurrences of point are in texts where the point is that is repeated. 75 of problem are in texts where problem is repeated. And then compute as a point of reference, compute an expected repetition frequency. So if we had a binomial distribution, if they were just randomly distributed across the documents, how many instances we would find with repetitions. And as you can see, for instance, here for point, we would expect 100 occurrences in documents with repetitions, but actually it's 157, more than half as much again as expected. So that's an indication that there is indeed some term clustering. Interestingly, this led me to change my attitude towards 2 of these candidate nouns for lexicalization, because reason, one of the less frequent ones, actually doesn't show any indication of term clustering. There are 9 occurrences with repetition. You can see the 95 instances are spread across 90 different texts. There's very little repetition, and these 9 repeat occurrences in repeated documents are just what you'd expect by a binomial distribution. So because reason doesn't show term clustering, I exclude it from the list of candidate lexicalized expressions. On the other hand, trouble has 18 occurrences in repetitions against less than 4 expected occurrences, which is a very large ratio, more than a factor of 4. And for that reason, I include trouble in the list, which gives me the final list of potentially fixed expressions in the shell noun construction, which is point, problem, thing, fact, and trouble. Okay, so we analyze these as lexicalized subconstructions. That's mainly linguistic analysis. I'm going to skip that in a moment. But more importantly, we exclude these from the productive construction. And because if they are lexicalized, then they are not part of a regular productive pattern. And I'm going to show you later on that it was important to make this exclusion, that we get much better, clearer answers for other aspects if we exclude these lexicalized ones. Here's a visualization of that. So that's our frequency distribution and the corresponding zip plot. Now we changed it so that the red and green ones are assumed to be lexicalized subconstructions, polysemous in red, and the other lexicalized ones in green. And the blue nouns, they are understood as part of the productive shell noun construction. Now, take a close look at the zip ranking. Recall that the top nouns don't fit the Zipf-Mandelbrot law. If I do the same plot for the productive constructions as the nouns indicated in blue, then we get a very good fit. So now it's actually, the productive construction is actually perfectly in line with Zipf's law, which again is a good indicator that this was the right choice, so that we now actually have a productive pattern characterized by Zipf's law. Okay, so these additional, can skip the linguistics, let's get back to the mathematics, because they're going to get a little bit more sophisticated or more complicated now. So how do we measure the productivity of the construction, the sort of the low frequency end? Well, the main indicator of productivity, of course, is this bottom end of the frequency distribution, where we have these bars of apex legomena and dyslegomena. Because of the discrete frequency counts, we have these show up as horizontal bars. So the bar marked by the green arrow, that's actually these, how many were 180 or so apex legomena that we have. It's 180 dots that are actually merged into a single bar because of logarithmic scale. Now, clearly, the Zipf plot isn't a good way of looking at the bottom end. It's very good for looking at the top end of the frequency of Zipf's law, but not very good for looking at the bottom end. So a better statistic is what we call the frequency spectrum, which just counts how many apex legomena there are, how many dyslegomena there are, etc. So V1, that's the number of types that occur just once in a sample. The apex legomena, V2 is the number of types that occur twice. And generally, Vm is the number of types that occur exactly m times in a sample. It's basically the logarithmic plot just with axes flipped and different scaling. And the key indicator of productivity, thus, is the first bar we see marked with a green arrow. That's the number of apex legomena we have. And putting that in relation to the rest of the frequency spectrum, that's our main indicator here. This is one approach that we've taken, that's sort of the more mathematical approach to productivity. A more intuitive approach to productivity is to look at so-called vocabulary growth curves. So what you do is you look at the first 100 tokens in your sample, you count how many distinct types there are among those first 100 tokens, then you look at the first 200, first 300, etc. And if you plot the number of tokens on the x-axis against the number of distinct types of the y-axis, you get these characteristic growth curves. So the intuition is the more productive a phenomenon and process is or pattern is, the steeper the growth should be. Because then we should see more distinct types. So the higher the curve goes and the steeper it climbs, the more productive. So this has been used as a very intuitive approach to assessing productivity. It's also been used as a mathematical approach because somebody, Harald Bayern, a very famous linguist, came up with the idea that we can use the slope of this curve, of this growth curve, as a measure of productivity, which he called Bayern's productivity index, strip P. Interestingly, it can be computed, so you don't actually have to estimate the slope of the curve. Under random sampling assumptions, it's actually the number of apex legomena divided by the number of tokens. So this index actually became very popular because, unlike all of you, linguists didn't immediately notice the very obvious problem this has as a measure of productivity. if you look at the curve, the slope, of course, decreases with increasing sample size, which means this measure of productivity depends very much on how large your sample is, which makes it completely unsuited. It's very difficult to judge the value you get from a productivity index because it depends on sample size, and it's almost impossible to compare two different samples of different sizes because you can never tell, or it's very hard to tell whether a difference in the productivity index is due to different sample sizes or due to an actual difference in productivity. So of course, people came up with other equations that, well, one is the type token ratio. That's always been very popular in the humanities. And then various other coefficients and laws that try to avoid this sample size dependency. But in the end, at the end of the day, all of them are problematic, either because of sample size dependencies. And this is work I carried out actually 10 years ago or so, where I carried out simulation experiments. So in order to understand how these measures behave, one very interesting approach is that you generate a synthetic population of types that follows Zipf's law, and then you can control the parameters to make the population more productive or less productive. So here the different colors, the red line is a population that I consider very productive. The green and blue lines are less productive populations, basically based on this sort of Zipf slope of the frequency distribution. Now, if I simulate, I generate random samples from this population and then compute productivity index or type token ratio or other measures for different sample sizes. You can see here what happens. So you see there's a strong sample size dependency for all these measures, but the bigger problem is that the lines cross. So if you look at a very small sample, so here this is actually token type ratio, so larger values are less productive. If you look at a very small sample, the red population seems less productive than the other two. If you look at a large sample, it seems much more productive than the other two. And you can also, with such simulation studies, you can also look at other effects or other distorting effects that you can have for these measures. For instance, if there are few lexicalized types in a sample with a very high probability, they distort the measures as well. So the x-axis here is the proportion of frequency mass of a small number of lexicalized types. And you can see how much these measures are affected by this proportion. And that's not what we want to measure. We want to measure the productive part of the frequency spectrum and not these lexicalized types. So these are all problematic. My solution is to turn to models that were also introduced into linguistics by Harald Bayen. He called them LNRE models for a large number of rare events. Basically, it's modeling type token statistics based on Zipf's law. If you look at this fit of Zipf's law again, so that was just basically fitting logarithmic frequencies with least squares fit in logarithmic frequencies. It looked very nice in a higher frequency range, but if you go to the bottom end, the red line doesn't really describe the actual data frequencies very well. And that's the productive part. That's where we see productivity. So having a model fitting a model that doesn't fit the low end doesn't make sense. And that's why the LNRE models, these are statistical models that assume a Zipfian population. These are actually fitted by matching an expected frequency spectrum, the expected expectations for the frequency spectrum to the observed frequency spectrum. That's what you see here. If you can tell the colors apart, the gray bar on the left, that's the actual frequency spectrum, the number of apaxes and dyslegomena, etc., of the Shell-Nahm construction. And the red and green bars next to it, these are the expected spectrum sizes or the expected spectrum for a fitted model. So you can see we get a very good fit to the frequency spectrum, and it's based on that. And because we're fitting mostly based on the apaxes and dyslegomena, we get a model, that's the green line, which doesn't work as well in the top part of the frequency, for the top frequencies, but works very well. It gives a very good fit for the bottom end for the productive part. And so I argue that that's the best way of measuring productivity, focusing on the bottom end of the frequency spectrum and basically taking the slope of this green line as a measure of productivity. The slope of the line happens to be the exponent a in Zipf's law. As I said, it has to be larger than 1, because if we have an infinite population, infinite number of types, then this can no longer be the probability. So pi I are the type probabilities now. So the frequent values have to add up to 1, and we cannot normalize if a is less than or equal to 1. But the closer a is to 1, so a smaller value of a indicates higher productivity, because then we have a less steep slope, which means that we have larger numbers of apaxes at the bottom. If you have a very steep slope, a up to infinity, 2, 3 up to infinity, then we get shorter ranges of apaxes in this legomena, which indicates a less productive process. So my argument is that this is actually a very good measure. I promised to show you why it was so important to exclude the lexicalized types. So this is the fit we get for our LNRE model, which isn't perfect, but reasonably good even for the high frequency items. If I fit the same LNRE model to the entire data, including the lexicalized subconstructions, it looks like this. It still fits the bottom end nicely, but at the top end, it's much further away. So it accounts much less well for the data than the model fitted to the productive construction. So even for this mathematical reason, in order to fit relatively simple mathematical models, it's important to exclude these lexicalized items because they have such a distorting effect. Okay, so that's how the model actually works. Does everybody recognize the Poisson distribution? So actually, this is the expected, size of frequency class M. So how many types have a frequency exactly of M? The Poisson distribution here is the probability. So pi I, as I said, I is an index for the vocabulary items, for the types in a vocabulary in the population. S is the vocabulary size of the population, how many distinct types there are, not in the sample, but in the underlying population. This could either be a finite value or infinity. And then here we have a Poisson distribution, so the probability that type number I with occurrence probability of pi I occurs exactly m times in the sample. The Poisson distribution makes things a lot easier. Normally, we'd have to use a binomial distribution, and probability distribution would be binomial, but the Poisson distribution simplifies the maths a little bit. And sort of by adding up the probability of each type occurring exactly m times, I get the expected value of the number of types that occur exactly m times. And similarly, basically by taking 1 minus the expected number of types that don't occur in a sample at all, I get the probability or the expected vocabulary size V. And this is actually how this fitting was done, how we computed expectations. In the same way, we can also compute or estimate variances, which is the basis for goodness of fit tests and other hypothetical tests, and for computing vocabulary growth curves with prediction intervals. So we can do standard stats with these LNRE models. One thing I don't like about them is these discrete sums and also the Poisson probabilities, because if you have to sum over 1 million distinct types in a large population, then of course you run into numerical problems, and it's also computationally relatively expensive. So what we actually use are these discrete formulations, but a continuous approximation, and this is where things get wild. But since I'm not a real mathematician anymore, I can do such stuff, which is that we replace the discrete type probabilities by a continuous type density distribution. So that's a distribution over the probability parameter pi, and the integral under this type density, that's the type mass in a certain probability range. which means that W1 is the most frequent type, the first type. This is actually spread out here in this continuous distribution in a probability range between 0.28 and 0.5. The second type is also spread out. This is the third type. So basically, this is the part of the curve whose integral adds up to 1. This is an integral of 1, an integral of 1. And that's how we obtain basically types or approximate types from a continuous distribution. And the probabilities of these types are obtained by summing pi times the density g of pi. So we get the probability values for these types here. And you can show, again, using approximations, you can show that the equivalent of the Zipf-Mandelbrot law is given by a power law for this type density distribution with a parameter alpha, which is just the inverse of the exponent a. So basically alpha is between 0 and 1, and that corresponds to 1 over a. So we can use that very easily to assess productivity. Big advantage is that with this approximation, we can turn the discrete sums into integrals. And does anybody spot what kind of integrals these are? These are actually gamma integrals, so we can easily evaluate them in terms of incomplete gamma functions, for which we have efficient and fairly accurate algorithms. So this is something that's much easier to work with. Okay, but now to the results we get from these LNRE models. So here I use the LNRE modeling in order to try and assess whether there are differences between the three shell noun classes that we wanted to focus on: factual, mental, and linguistic. So here, because I've excluded the polysemous nouns, I can assign each noun and each instance of the noun uniquely to one of the shell noun classes. That means I can now introduce three separate subconstructions for factual shell nouns, mental shell nouns, and linguistic shell nouns. Here are vocabulary growth curves for these classes. Are there differences in productivity? Are there an answer I expect is exactly what I get? I couldn't tell. So they are all productive because the curves grow fairly steeply. There are different lengths. Clearly, the mental class grows faster than the linguistic class. But the sample size is also a little bit larger. The factual class seems to be fairly similar to the mental class, but has an even larger sample size. So it's very difficult to decide here. But if we now apply the LNRE models, estimate LNRE models, and look at the Zipf slopes, then we find that there's actually no noticeable difference between mental and linguistic. So we have slopes of a equals 2.9 and versus 2.83, even though the mental class looked more productive, had a faster growth of the vocabulary than the linguistic class, whereas factual actually has a lower slope of 2.28, so factual appears to be more productive. And the key reason here is that if you focus on the bottom end, on the apex and dislocated, then you see that mental and linguistic have the same degree of productivity, but they differ in the top end of the frequency spectrum. So the linguistic class has a few relatively high frequency items, whereas the top items in the mental class have lower frequencies. And that changes the shape of the growth curve so that the growth curve for linguistic appears to grow slower than for mental, even though the actual productivity is the same. So based on this has actually given us a new insight or a different perspective on differences in productivity. I'd like to stop this part, this second part of the talk now, but I can't, because I have to admit that what I didn't check, of course, is how accurate model estimation is. So basically that's a single, it's optimization fitting observed to expected frequency spectrum, but how reliable is that? This is very difficult to work out mathematically. So what we do in Corpus and computational linguistics is we turn to simulation experiments. Basically, what I did was parametric bootstrapping, using an estimated model, generate random samples, and then re-estimate the model parameters, which unfortunately, that's the first plot that doesn't work properly on this machine. This should be colored. but perhaps you can still make it out well enough. Again, so this spiker, that's the distribution of SIF slopes I get for the factual class, and the other two lines are the distributions for linguistic and mental. So as you can see, there's an enormous amount of spread. So for factual, we get SIF slopes between 2 and 3, whereas the ones I had for the actual samples was 2.23 versus 2.8 or 2.9 for the other classes. So that's clearly not a significant difference if you see at how much uncertainty there is. But we do see that linguistic and mental are almost identical. So there's clearly no difference there. Whereas we have some indication that factual might have a different productivity than linguistic and mental classes, but we don't have enough evidence. We don't have statistically significant evidence. Okay, so that's what we can find out about the productive part. And now let's end by looking at the middle, by looking at associations between nouns and constructions. As I mentioned, what we're looking at here are collocational patterns, known as collocational patterns in corpus linguistics. And there's a very well established, again, very simple quantitative approach to identifying such collocational patterns, which is to compare the frequency of a noun in the construction with its frequency outside the construction. And if its frequency inside the construction is unusually high, higher than outside the construction, that's an indication that's somehow attracted to the construction. Actually, that's the concept, what I'm describing is the concept of statistical association. And association measures are a staple of corpus linguistics. It's one of the most central quantitative concepts, even though it's such a simplistic concept, it's one of the most central quantitative concepts in corpus linguistics. Now, the mathematical representation of these data, frequency inside and outside a construction, is of course a 2x2 contingency table. The left column of the table is for instances of the construction. The right column are all other occurrences of nouns in a corpus outside the construction. And then we pick one candidate noun at a time, say reason. We get the frequencies of the noun inside and outside the construction in the first row, and the cumulative frequency of all the other noun types in the second row. And then basically by comparing the two columns or two rows of the table, we can assess whether frequency in the left column is higher than the relative, significantly higher than the relative frequency in the right column. So basically, we often refer to that as the observed contingency table or contingency table of observed frequencies. It's actually an association between a given word W, first and second row, and a construction here indicated by CX in the first and second column. In order to assess whether a given contingency table is an indicator of, shows an indicator of association, we need a baseline, which is the expected contingency table under the null hypothesis that there's no statistical association, in other words, that the word and the construction are statistically independent. In that case, the chance of getting the noun inside the construction is a product of the frequency of the noun, the relative frequency of the noun, P1, and the relative frequency of the construction, P2. And then you can work out the expected frequencies for all cells in the contingency table with these equations. The key to focus on, of course, is the top left cell, the co-occurrence frequency of noun in construction compared to the expected co-occurrence frequency. And now we just need some sensible mathematical equation to quantify, compare the two and quantify the result. Unfortunately, when I wrote my PhD thesis on the topic some 20 years ago, people had already come up with 57 different equations, and they have kept busy since, and I think now we must be up to 100 or more suggestions that have been made. So these range from very intuitive approaches, such as mutual information. It's actually derived from the information theoretic concept of mutual information, but simply put, it's the ratio between observed and expected co-occurrence frequency, and then a log transform, a binary log, to get it, to express that as bits of mutual information. Because people realize that these tend to overestimate association for very rare nouns, they just started multiplying the observed co-occurrence frequency either in the numerator or with local MI, just multiply the entire MI value by the observed frequency to just counteract the flow frequency bias. Then there are various measures derived from statistical hypothesis tests applied to the O versus E comparison in simplified form, or applied to the full contingency table, which is what every self-respecting mathematician would start with, chi-square test, likelihood ratio test, or possibly Fisher's exact test. And then there are some other coefficients that are measures of effect size. What I did in my PhD thesis was part of my PhD thesis was to take a closer look at these and try to understand, are there really differences between those measures? And if you look closely, there are enormous number of connections. So some measures have totally different derivations, but have the same components in their equations. Some measures are just sort of z-score and chi-squared, are the full contingency table versus the one cell version of the same measure. Then there are two entirely different equations for chi-squared from two different derivations of the test, but which turn out to be exactly the same value. And then you get all these other connections. So it's all a mess of interconnections. And sort of my result was to group these many measures into 3 or 4 major groups and recommend one measure from each of these groups as a sort of ideal or optimal measure. That was 20 years ago. By now I've gained new insights, so I no longer stand with this. But let's use log likelihood as a very popular measure and one of my recommended measures to assess statistical association. So I've calculated a log likelihood association value for every noun in the sample, for every of the 308 productive noun types, which will be shown on the y-axis. On the horizontal axis, for comparison, I have the occurrence frequency of the noun in a construction. So that's the 011, the co-occurrence frequency. And if you could see the plot, then you would actually see a distribution around here, that there's a very strong correlation between frequency and log likelihood scores. And that's what the blue oval actually is intended to show, which means log likelihood isn't a very useful measure by itself because it's so strongly correlated with frequency that it doesn't give us a lot of new information. One thing that people have used log likelihood for is as a significance filter. So basically, you can find a standard of chi-squared thresholds. And so in this case, if a significance cutoff after applying corrections, Bonferroni corrections for multiple testing, a chi-squared value greater or equal than 15.6 means that we have a significant evidence for an association for an item. So any points imagine or look at the PDF slides later on and imagine the points in the green range, these are actually the significant ones where we have significant evidence. Okay, and I think we can skip over this fairly quickly. Here we would see the same for mutual information, highlighting that mutual information has this extreme low frequency bias. So you get very large mutual information values for frequencies of 1 or 2 for the apex and dyslegomena, which is something we don't want. But there's a range of green points. Imagine there are some green points here. These are the ones that are significant according to the log likelihood significance filter. And sort of this is one way of picking this out. And finally, there is my favorite measure you can't see, which is basically a conservative estimate, conservative confidence interval estimate for mutual information. I call this measure conservative log ratio or LRC. I like the measure because it combines the significant aspect and the significance aspect and the effect size aspect we get from mutual information. And actually it's done in such a way that any positive log ratio score means it's also significant, because that means we have significant evidence for mutual information value larger than 0. Okay, and this actually gives us a fairly reasonably looking distribution of nouns that seem to be associated. And I've also we can also look at the different classes. So again, here we would have the distributions for these different classes. These plots, they are not very interesting because they don't look much different. So we can't read any differences between the shell noun classes, but what we can do is to look at the most strongly associated shell nouns for each class. And so for the factual class, for instance, I've excluded the very frequent ones because we still get a frequency correlation here. So for instance, for the factual class, we have snag, curly, drawback, upshot, essence, downside. For the mental class, rationale, inference, worry, consensus. For the linguistic class, it's the guess that, the justification that, the objection that, etc. So I think they also sound very natural in these, or they sound fairly typical examples. So this is clearly shows that the collocation ID works. There are fairly good collocations in these constructions. An interesting perspective, which finally brings us to deep learning and AI, is that we could also look at whether there are, so this is one aspect. The other aspect of association could be semantic patterns in these. So whether they are semantically similar, and indeed some of them seem to be. If we look at what we see here are the strongly associated nouns for the linguistic class: criticism, response, reply, message, story. And as you can see, this is a semantic map. So based on word embeddings from a large language model, or not so large language model at the time. But that's good enough for this kind of application. So you can see that many of these cluster together. They're actually very similar nouns that occur in this shell noun construction. If we do the same for the mental class, then we see a different pattern, because here we have actually two main groups. Down here we have the rationale, understanding, assumption, theory, consensus, opinion. So these are really sort of information related as mental aspects. Up here there's fear and worry, concern, feeling. So these are actually more emotion related aspects. And that's very interesting evidence, also quantitative evidence that feeds into the linguistic analysis. Okay, and now I can come to a slightly long conclusion. So this should get us just through the 90 minutes. I hope I've managed to show that we have ways of analyzing the fixedness productivity continuum, at least for single variable slots in lexico-syntactic constructions or patterns. We've seen different indicators of fixedness, of productivity, of association, many of them mathematical or quantitative. Others, such as the semantic clusters we've just seen for the association patterns, for the collocations, or semantic regularities in productivity assessment, or the polysemy in fixedness are more linguistic correct properties. But as so often in corpus linguistic research, the linguistic aspects and interpretation and the quantitative mathematical model have to work hand in hand in order to get clear conclusions. Now, learning about individual slots. So this was more or less an exercise in trying to understand what's the right mathematical approach, is how much can we learn from the corpus evidence. But of course, linguistically speaking, it's not all that interesting. So the bigger picture that's actually behind that is, on one hand, that we would also want to look at correlations and patterns that are across multiple slots. If you think of the X is the new Y, there are certainly certain correlations between the X and the Y slot, and exploring these would be a very interesting extension. But the main work we do is actually the reason why this entire study is part of a PhD project in our research training group, which is focused on comparisons of candidate constructions. So how do we decide whether something is a construction or not? And these measures for individual slots, that's one aspect or one first attempt to find quantitative evidence for that. So if you want to learn more, there's a link to the PhD project, description of the PhD project. It's called Corpus Evidence for Delineating Constructions. And if I may, I want to give you a very brief look at how we approach this problem of delineating constructions, which also shows you a bit how we are actually working with data. And what I've done for single slots so far uses the same kind of data representation. So this is actually a standard transitive verb pattern. That's from the earn somebody something, earn somebody something example. So we have a main verb, a subject dependent on the verb, an object noun, and a possible adjectival modifier of the object noun. So that's just a part of sentence structure of code, but that's the first decision we have to make. So we start with a syntactic pattern, and then we can extract the corpus data in tabular form. So each line is one instance of this pattern, and we represent it by the fillers of those items. So the first line is something like they earn money. So we have they earn, no adjective, and an object noun money. He earned a chance, the manager earns, without any object specification, or the managers could be managers earn. I earned my first salary, Jane earned much sympathy, and yeah, etc. So that's how we actually represent the data, and all the mathematical analysis happens in this tabular representation. And then we can write patterns. I call these lexico-syntactic patterns because they're not necessarily constructions, but such patterns express hypotheses on potential constructions. The first pattern, earn money, that's the combination to earn money. The dots mean that the subject and the adjectival modifier are arbitrary. They can be absent, they can be present, they can be anything. So it's just a combination of earn and money. That's what we consider a collocation in corpus linguistics, a typical combination. If that's seen as a construction, it would be a collocational construction. Same for workers earn something. Here's a three-way collocation to earn good money. And that's actually something that's relatively frequent because it's a more or less fixed expression. Here's an example, earn one's keep. To earn one's keep, keep can't be modified by an adjective. That's what we indicate with the X here. And then we can have also constructions with variable slots. So somebody earns someone some kind of support. This would say that the subject has to be a pronoun, he earns or it earns, and there has to be an adjective there, but the pronoun itself and the adjective are unspecified, so these are variable slots. And that's also a hypothesis. And the question is now, which of these hypotheses should be seen as constructions and which should not be seen? And sort of the main indications we expect to find are association patterns. For instance, whether earn good money is a construction might depend on the association between the potential building blocks earn money and good money. So the question is earn good money an expression in its own right, or do we have two collocations, earn money and good money, and we just see earn good money because people combine the two? If there's an association here, that means the frequency of earn good money is much larger than we'd expect from a random combination of the two. That's an indicator that it might be associated and thus might be a construction. And of course, that also applies to the two-word constructions, two-word collocations made up from two individual words, or even to larger units to delineate the construction from even larger constructions. And the other aspect we need to look at are generalizations over the slot. So earn good money is a completely lexicalized construction. So the subject is arbitrary, but the three specified elements are lexicalized. Two potential hypotheses we might have is either that it's some kind of money, so that you need, and that's pos here means it's an adjective with a positive meaning. Earn good money, lots of money, grand money, or something like that. So that's an adjective expressing a positive evaluation or positive scale. That would be one hypothesis for more general construction. And the other is the construction that you can earn good and then use not necessarily the word money, but any concept, any term that refers to the concept of money. Earn good dough, earn good dollars, etc. So, and then again, the question is earn good money a completely lexicalized construction by itself, or is it just one instance of the earn good and money semantic class construction or the earn pos money construction, if these are constructions? And this is where the other two aspects come in, because the main indicator of whether these are constructional, that would be the fixedness productivity continuum of the single slot. So everything I told you about the shell noun construction today applies exactly to this case, where we would especially focus on fixed items is good or money are these Do they look like fixed items within the this frequency table? And is there evidence that there's a productive construction here because it's a large? If there are only two distinct adjectives that we ever see in this construction or in this pattern, then then it's probably not a construction. It's just two separate lexicalized instances. But if we have a productive range of adjectives, then it's more likely to be construction. So that's kind of the bigger picture we're working on. And then, of course, the same at this generalized level, I can also build constructions from smaller parts. So association also comes in, and we've got this very, very complicated network. My PhD student, Madin Patel, isn't going to finish that within the next 10 months. But I hope to have another PhD project after that, which will become increasingly mathematical and challenging as we move through the research training group. My very last slide. Of course, I hope that we can also collaborate within FAU MoD or in other groups on this research, because there's a lot I need help with. Of course, it would be good to have a more sophisticated statistical analysis, perhaps more sophisticated model than, say, these LNRE models with their simple continuous approximations. Perhaps there are ways of estimating productivity more reliably from relatively small samples than the LNRE models. As we've seen, there's this enormous sampling variation. Perhaps there are better ways of measuring statistical association patterns that aren't just because sort of all we do in collocation analysis is really based on this 2x2 contingency table. Sort of that's a very, very simplistic picture. Perhaps we can include semantic aspects, or there are more sophisticated ways that take additional frequency information into account in order to get a better picture, etc. And especially measuring correlation patterns across multiple slots, whether the productivities of different slots correlate in different ways. This is very challenging. We've tried to do that with copular functions, but it's very difficult to formulate a sensible model for that. And of course, there's my real overarching research program. So what I really want to do in the next 10 years, or the 14 years I have until retirement, which is to develop the approach of digital hermeneutics. So hermeneutics is the art of interpretation in humanities. And the idea behind digital hermeneutics is that actually it's what we have done all the time in Corpus, linguistics, and digital humanities and many other fields, that we try to integrate human interpretation of the results, which is when we look at this and interpret results, with quantitative methods and the mathematical analysis. And I think people usually aren't aware of that they're doing digital hermeneutics. They just apply some visualization tool or some statistical method and then try to make sense of the results and find an interpretation. But actually, it's a process where both the quantitative side and human interpretation should go hand in hand. And achieving that, I've realized over the last 2 years that a lot of the work I've been doing all the time is actually kind of digital hermeneutics, is a way of in a very difficult way, trying to bring in some insights into the statistical analysis and also to make sense of the results we get from the quantitative analysis. So the two main challenges is to understand quantitative results. The more sophisticated the model, the harder it is to make sense of what it actually tells us at a linguistic level. And on the other hand, and that's sort of the main goal of my research, to somehow feed the human insight from interpretation back into the automatic analysis. One very simple way in which I've done that now is by excluding what I identified as potentially lexicalized constructions. I got a much better model of the productivity of the productive construction. So that's a way in which sort of my insights, my interpretation has fed back into the quantitative analysis. In some ongoing research projects, we do this integration already in a more sophisticated way. We also already have a closer integration where more of the linguistic insights feeds into the models. And since we started recently talking about the model discovery, I've been wondering whether there isn't a fairly close connection to model discovery hermeneutics. So thanks very much for listening, and I'm available if you have any questions.
Thank you.